Hello. In this lesson, we're going to kind of summarize all of the area formulas that we've found so far, and then we're going to put some of them together to find more involved shapes. So we're going to have to use some pieces together of what we've already found. So here's what we know so far. Here's areas of shapes that we've already calculated. We have found that the area of a parallelogram is base times height. We have found that the area of a the area of a square, this really should be marked out as equal sides, so they should be marking it like this to show that all sides of those are equal. Area of a square is s squared. The area of a rectangle is base times height. The area of a kite is 1/2 the product of its diagonals, diagonal 1 times diagonal 2. What do I mean by diagonals? Here could be diagonal 1, this would be diagonal 2. So I need to multiply those two lengths and then multiply by 1/2. Area of a circle is pi times the radius squared. Area of a trapezoid is 1/2 the sum of the bases. The bases are this bottom part and then its parallel top part. I need to add those together, multiply by the height, and then take the half. The reason we had that is because a trapezoid is half of a parallelogram. And then a triangle is half of another parallelogram, so it's 1/2 base times height as well. So there are all of the formulas of the things that we have derived thus far. What we're going to do is we're going to use some of them to derive more involved shapes. So what about if I had shapes like the following? What if I had a pentagon or a hexagon or an octagon? How would I calculate their shapes? Well, what we're going to do is use a very common idea in math, is break it down into more familiar pieces. And what if I broke them down into triangles? If I broke them into triangles, I could find the area of one of the triangles and multiply by however many triangles it takes to make up the piece. If it's a pentagon, 5 triangles. If it's a hexagon, 6 triangles. If it's an octagon, 8 triangles. Let's do the pentagon one. So find the area of the following pentagon. It's regular, meaning all sides are 2. And what I'm going to do is I'm going to find one of these triangles, and then I'm just going to multiply by 5. So let's look at this bottom triangle here, because the problem is I know that in order to find the area of the entire pentagon, I need to get the area of one of the triangles, and the area of a triangle is equal to 1/2 base times the height. I know the base of the triangle is 2, but I don't know the height. I'm actually going to have to use a little trig in order to get there. So I'm going to drop a perpendicular down because I need a right triangle in order to do trig. If this whole thing across is 2, it means to here to the middle point is 1, from the midpoint to the other vertex is 1. Now I need this angle, and I can actually get there if I'm clever because I can realize all the way around is 360 degrees. Well, there's 5 tips of the triangles in there, so 360 divided by 5 tells me that each of these is a 72-degree angle. If each of these up all the way across is 72, then that means this angle is half of 72. That is a 36-degree angle. And now I can do trig in order to find the height of that triangle. So I'm going to pop out like this purple triangle right here, and I'm going to do some trig on it in order to get its height. So purple triangle, this is 36 degrees. This is 1, and I want the height. I have the opposite, and I'm going after the adjacent. This is the opposite side. I'm going after the adjacent side. And which trig ratio uses opposite and adjacent? That's tangent, SOHCAHTOA. So this is the tangent ratio. The tangent ratio from my 36-degree angle equals my opposite, which is 1, divided by my adjacent, which is h. If I solve for h by multiplying up here and then dividing the tangent of 36 down, I get that h is 1 divided by the tangent of 36. And then I grab a calculator and I type in 1 divided by the tangent of 36. And I get that the height is like 1.38. So the height of one of these triangles is 1.38. So the area of one of the triangles, let's do AT to stand for triangle, is 1/2 the base, the entire base is 2, times the height we just found is 1.38. 1/2 times 2 is just 1, so 1.38 will be the area of one of the triangles. The entire pentagon takes 5 triangles, so the area of the pentagon will be 5 times the area of the triangles, which will be 5 then times 1.38. So 5 times 1.38 tells me that the area of the entire pentagon is 6.9. My units are just U, so 6.9 units squared, whatever my units would be. And that's how you do it. And that's how you do essentially all of the shapes after that. You break it down into triangles. You need to use trig in order to find that angle, because you have to use trig in order to find the height. You need to figure out the angle by just taking 360 divided by however many triangles you have. And the process kind of just repeats over and over again. Once you've seen one, you essentially have the formula to do the rest. You have the template. So that's how we could find the area of a pentagon. What we essentially just did is a very old Greek idea, and they actually developed names for this because they did it so often. So what that height of the triangle that we found has a name. It's called the apothem. So this h value that we just found right there, that's called the apothem. So the apothem for this one would be 1.38. The apothem is the segment drawn from the center of a regular polygon perpendicular to the side. It's essentially the height of each of the triangles that you would be finding. Why is it the word apothem? Because I told you the Greeks were one of the first to do this. It comes from the Greek apo, meaning away from, like apart, and then the Greek thema, meaning position, like our word theme, which is the central position of a story. So the apothem is the line segment that goes away from the central position of the polygon. That's where they get the name. We also realized that we needed to find the central angle in order to be able to use trig to find the height of that apothem. The central angle is the angle that is made with the vertex at the center and then the sides passing through consecutive vertices. What do they mean by that? So it's the angle made that goes through the vertex and then connecting consecutive vertices. So the central angle would be this angle right here. In our last case, that central angle was 72 degrees. So the central angle is essentially the angle at the top of all of those triangles. I end up needing to cut it in half in order to do trig, but I need to find what's called the central angle first. So the central angle is that right there. Let's find the central angle for some following polygons, and then we'll develop a formula. So what about the pentagon? We actually just did this a little bit ago, right? All the way around is 360 degrees, and there's 5 triangles in there because it's a pentagon, so it's 360 divided by 5. Each of the central angles then would be 72 degrees. 72 times 5 is 360 degrees. What about a hexagon? 360, if it's a hexagon, it's divided by 6, so this would equal 60 degrees. Which actually means a hexagon is very special, because if this is 60 degrees, it actually means that all of these are inside of here are equilateral triangles, because it's 60, 60, 60. So the hexagon is the only one where all of these are actually the same length. So this length is actually the same as that length, is actually the same as that length. It's the only one that it occurs for. The rest of them, that is not true. Octagon, there are 8 in there, so this would be 360 divided by 8. 360 divided by 8 gives me, that makes sense, a 45-degree angle. So each of these would be a 45-degree angle. Each of these right here would be a 60-degree angle. Let's use colors. So there's 60. Here is 72. So you can see they're getting smaller because you obviously only have 360 degrees to work with, and when you have more and more triangles, each of them is going to consume more and more, so the central angle gets smaller and smaller and smaller. What's the formula for it? Well, it's 360 divided by however many triangles there, and however many triangles there are is exactly the same as the number of sides of the polygon, so it's always 360 divided by n. If you have a 10-sided figure, each of the angles takes up 36 degrees for the central angle. We're going to practice just labeling and then finding some of these names. So in the figure below, a regular hexagon is inscribed. Inscribed means inside, with each of its vertices touching the edge of the circle. Inside of circle R. That's a symbol for a circle if you don't want to write out circle. Identify the center, the radius, the apothem, or any apothem, because there's a few, but there's actually only one marked here, and then a central angle of the polygon. Then find the measure of the central angle. So what is the center? The center is point R. What is the radius? The radius, there's a few, so you could go Rn, Rm, Rl, Rk, all of those would work. So Rk would work. It's a segment, so we should probably put the segment symbol above it. An apothem, well, there's only one clearly labeled. It's Rs, so Rs would be the clear apothem here. There are others, but they haven't been constructed yet. and then name a central angle and find it. So there's a few central angles. You could go KRL, you could go MRN. Either one's fine. Let's go MRN, angle MRN. Then they ask us to actually find what the measurement of that angle is. So what is this angle? Well, its measurement would equal 360 divided by however many sides there are. They said it's a hexagon, so it's 6, which means that that is going to be a 60-degree angle. There is an area formula for the area of a regular polygon. If you want to use it, it's essentially exactly what we did. You find the area of one of the triangles and you multiply by however many triangles there are. Let's see why the formula that the book gives is actually the exact same as what we did before. So the book says if you have a regular polygon, you can find its area by doing 1/2. A is the apothem, and then you multiply by n. N is how many sides there are, times s. So let's look at just this first one, because they give two formulas. We'll show why they're the same here in a moment. Why is the first one true? Well, let's go looking. Area equals 1/2 a times n times s. Let's just write that out. Area equals 1/2 a times n times s. You don't necessarily need the parentheses. These are all just multiply in between. I'm going to rearrange these things. So this is really 1/2 times a times s times n. That's the same thing. Now look at this though. What is this? 1/2 a times s. Well, a is the height of the triangle and s is the base of the triangle. So this is just the area of one of the triangles in there. So this is equal to the area of one of the triangles. So it would be the area of, I didn't want to use red because they use red. Let's do purple maybe. Purple. It would be the area of this triangle right here. And then I need to multiply by however many triangles n there are. That's exactly what we did. So hopefully you see why this is exactly what we did. It's the area of one of the triangles, then multiply by however many triangles there are. If there's n sides, there's going to be n triangles. Now, where do they get this formula from? It's the same as doing 1/2 times the apothem times the perimeter. Well, realize this. Let's do the pentagon just as an example. So if it's a pentagon, there'd be 5 triangles. Imagine that I unrolled, like I snipped the pentagon and I unrolled it. So if I unrolled it, there'd be 5 triangles in there. So 1, 2, 3, 4, 5. Right? You could kind of see it. 1, 2, 3, 4, 5. I'm just going to unroll them, but keep all of their sides still connected. Okay? Well, how would I find the area of this? Well, we just did this a second ago. The area of this would be 1/2 the areas of these triangles. Well, what's the areas of the triangles? The areas of the triangles are going to be the apothems. So the apothem A, apothem A, apothem A, apothem A, apothem A. So 1/2 A, and then times n times s. Each of these have side lengths s, 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 I think is what they call them. Yep. And then we multiply by n. But check this out. What is s times n? S times n is just the perimeter, right? All of this right here is just the perimeter. If I take the length of one of the sides and multiply by however many sides there are, that's just going to be the perimeter. So this is just the perimeter right here. So I could just instead do 1/2 times a, and then instead of doing n times s, just multiply by the perimeter. And that would be the exact same thing. So it's just two different ways of writing the exact same expression. It's just how you view it. So that's why both of those are true. If you want to use these formulas, you can, or you can just think about find the area of one of the triangles, multiply it by however many triangles there are. I think that's better because that's the real concept instead of just memorizing a formula. But these are where the formulas come from. Okay, we're going to use it. Find the area of the hot tub cover that would be needed in order to cover the following hot tub. So we've got a hexagon here. Let's find one of the triangles. So we're just practicing this right here. So, right, let's draw in all of them. So, right, we've got all the triangles in here so we can clearly see them. Now let's find one of them. Okay, let's find this guy right here. So this is 5, that's the base. Now I need to find the apothem. I need this right here. Well, we know that this is 60. We did that earlier. This is 60. All of these have central angles of 60, which means that there to there is 30. That's what's going to allow me to find the apothem, because if all the way across is 5, then from here to there is 2.5. So my triangle looks like this right here. This is 2.5, this is 30, and I want the apothem A right here. So I'm going to use some trig. I've got opposite, which is 2.5, and then the apothem is the adjacent. That's convenient that they both start with A. Which trig ratio am I working with? Tangent. It's always going to be the tangent when finding the apothem. So the tangent from my 30-degree angle will equal the opposite, which is 2.5 divided by my apothem A. I can solve for A by multiplying and then dividing by tangent of 30, so the A multiplies up, the tangent of 30 divides down, so I get 2.5 divided by the tangent of 30, the apothem. And you can kind of see a formula here now. Here's a formula you could really, because you're going to do these steps over and over again that are the same. The apothem is actually always equal to half of the base, because it always gets cut in half, so this top number is always a half, and then you always divide by the tangent of half of the central angle. So the apothem's formula, if you kind of recognize this already, is always going to be 1/2 of the base of the triangle's length divided by the tangent of half of the central angle. Hopefully you see that. If you don't, you got to just rederive it over and over again. But you're going to be doing the same process. 2.5 divided by the tangent of 30 tells us that this apothem is 4.33. So that's the height of one of the triangles. So now, what would I do? Let's find the area of the entire hexagon is going to be 6 times the area of one of the triangles. But now we know the height, and we can do it. Area of the hexagon will equal 6 times one of the triangles is 1/2. The base of each of the triangles is 5 all the way across, so 5 times the height we found is 4.33. Now I just run it. 6 times 1/2 times 5 times 4.33 tells me the entire cover is about 64.95. We'll say it's pretty much 65. It's got to be feet, I would imagine. Yep, 65 square feet. 64.95, but I'm rounding it because it's so close. And they're probably going to measure that as to the nearest square foot anyway. So about 65 square feet. There you go. I'm going to ask you to try one. There's only one today that I'm asking you to try, and you're going to do it for the pentagon, the literal pentagon. So first find the central angle, then find the length of the apothem. You're going to have to use some trig in order to get that. Then find how many square miles is covered by the pentagon. So I took a Google image overhead picture of the pentagon and then measured what each of the sides are of the pentagon. Each of the sides are almost a mile long, which is crazy. So the pentagon covers a lot of square miles. Well, not a lot, but it's a lot of area. So there you go. Follow the following steps. Tell me how much ground is covered by the pentagon in terms of square miles. And then come back to see how it's done. Okay, let's go over it. First thing I asked you to do is find the central angle. That'd be 360 divided by 5. We've done that before. It's 72 degrees. Find the length of the apothem. When you set it up, it'll be tangent of 36 is equal to 0.35. A then will be 0.35 divided by the tangent of 36, which is about a 1/2 mile. So from the center to the edge is about a 1/2 mile. And then the total square mileage of the pentagon is about 1 square mile, 0.845. But that's huge if you think about a mile by a mile. That's a lot of ground to cover. So there you go. That's how much square miles the pentagon takes up. Last part of this section is what's on what we call composite figures. Composite comes from multiple, like that's where we get the phrase composite figures. It's figures that can be separated into regions that are basic figures, multiple other figures. So it's shapes that are made up of triangles, rectangles, trapezoids, and circles combined or punched out. So this shape right here is obviously, you would find the rectangle and add on the triangle. This one you'd find the kite and subtract out the circle. This you'd find the 2 rectangles and add on 1/4 of a circle. This one you'd find probably the rectangle, subtract out half the circle, and then add on the triangle. So that's what we mean by composite figures. In the shape that we're doing right here, there's a blueprint for a mini golf green is shown below. How many square feet of carpet will it take to cover? So first off, what shapes do you see? I see a rectangle, I see a triangle, and I see half of a circle. So let's find them. half of the circle. So the circle has a radius of 4. So pi times the radius squared is 4 squared divided by 2. The triangle here is 1/2. Its base is 4 and its height is 4.1 shown. The rectangle here is its base is 4 and its height is 7. So length times width, 4 times 7. And then I just run it. 25.13 plus 8.2 plus 28. It would take just over 61 square feet of that AstroTurf carpet in order just to make this mini golf hole. So that's how we calculate composite figures. You just cut it into shapes that we already know how to do. Sometimes you're going to be using addition and sometimes you're going to be using subtraction. So identify which ones would be best to do by addition and which would be best to do by subtraction. Essentially, if there's something punched out, you're going to be doing subtraction. So this one would be addition. Rectangle plus triangle. This I would do three rectangles added together. Rectangle top, rectangle side, rectangle bottom. Add them together. This one I would do kite and then use subtraction, subtract out the circle. This one I already talked about. I would do rectangle, subtract out half a circle, then add on the triangle. So this is a combination. You have to do addition and subtraction. And that's it. Thank you very much. Have a good one.